I'm Mike Leach. I've been working on for probably over 16 years now, mainly on debug and trace. For the last 2 and a bit years, I've been an assignee at Linaro, working on a project called OpenCSD, which is a trace decoder, and doing a bit of work on CoreSight drivers and just generally getting CoreSight working on Linux. So what I'm going to talk about today, there's 3 small topics I'm looking at. First is AutoFDO. This is where we use trace to create profiles of an application and then feed them back into the compiler to get better performance. Secondly, I'm going to be having a quick talk about cross-triggering and complex use of CoreSight beyond what you normally get just running the ETM. And finally, I'm going to have a look at where we're going with the software development and have a quick look at a recent hardware specification that IMS is producing. So first of all, FDO, or feedback directed optimization. As I said, this is primarily a method of profiling an application and using that profile to better optimize the application. AutoFDO is actually an open source Google project which automates some of this and generates profiles that can be based on tracing a running system. It was originally used Intel PT and branch targets, but we've now adapted it so we can use CoreSight as the input for the analysis. So the first step is to gather the trace. You can use production binaries. By this I mean the binaries don't have to be have additional code in them to gather the information. Analyze using the Google tools, and then use that profile from the AutoFDO tools to optimize using the standard set of compilers. Initially, we had, as part of the OpenCSD project, a Linux tree where we were putting patches that weren't yet upstreamed for the development of CoreSight. We got some contributions which updated the inject command for perf, which is what is needed to generate profiles, and this was a key part of AutoFDO. What we find is that if you use a full ETM trace, it generates a large amount of data, and this was causing issues with decoding and analyzing the data, and the results from the AutoFDO process were basically very poor. Quite often you couldn't tell any difference between pre and post profile application. So the tools group in ARM did a bit of research into this and looked at it. What we found was that the best profiles could be created if you used sampling of trace data. So we needed to update the ETM so that it would generate sample data rather than data throughout the trace run. So we used the counter and sequencer features of the ETM hardware, and this allowed us to record small slices of the trace data, which we called strobing, and this pretty much conforms to what Intel do with PT and branch targets when using AutoFDO. So at present, the strobing feature is part of the ETM driver, but it's not controlled by perf. What we do is we have a record script that we provided as part of the demonstration system, and this will set up all the ETMs in the system and use perf to record the trace data automatically. So the first step is to create your application. It can be optimized, but you do need sufficient debug info to allow the trace decode to and profiling to match instructions with the source code. So we use the record script, and we set up the strobing to effectively do a small percentage, about 1% of the trace is actually captured. As mentioned, the record script also runs perf, and at this point it uses the per thread option in perf, which means we've got to ensure that the application being run remains on a single core. So once we've collected the data, we use the perf inject, which creates a profile. Then we pass the profile onto the Google AutoFDO tools. There's separate tools for the LLVM and the GCC compilers. Finally, using the compiler of your choice, depending on which one you started with, you feed the profile back into the compiler, and hopefully you'll get some improvement in performance. So in order to establish that this was working, we looked at running it on a high keyboard under the Android operating system. We found that AutoFDO works best on workloads that have got variable input data. So we chose SQLite, which has its own speed test, and we generated an initial test program using an O2 optimization. Now the results at the bottom here, the baseline profile is actually how fast it runs without any profiling at all. The A64 profile is the improvement when we use a profile generated from running trace on an ARC64. The x86 profile is in fact the improvement on the ARM binary if you feed the compiler with a profile generated on x86. So you can see here that the profiles actually are related to the source and the compiler as much as the more than the actual system itself. And finally, the PGO was the instrumented profiling trace, which we did for comparison. So all in all, we found that the results using AutoFDO and the methodology using the ETM in this strobing manner were very similar to the results that you get running the similar system on Intel and using Intel PT or the last branch record. So at present, if you want to actually try this out, first thing you're going to need are the AutoFDO tools. They're available on GitHub, obviously there. Do check if you look at this for any outstanding pull requests that ARM have been providing to that relate to generating ARM profiles. These are slowly being adapted by Google, but it's worth checking if you want to try this out. Secondly, you need the kernel with the necessary patches. The perf changes have all made it upstream and will be available from a 4.17 kernel onwards. The ETM patch that does the strobing, we've put on the perf OpenCSD GitHub, and that's available, or will be available shortly. I actually need to push it at some point. And that also contains the latest CoreSight drivers, which will also be shortly upstreamed. And in order to get this working on some of the more popular kernels, ARM is actually backporting sufficient patches for the CoreSight and perf to make it work with 4.9 and 4.14 kernels. Those will be available on public site. I don't know which one yet, but as soon as that actually happens, I'll put a list out on the mailing list, a message out on the mailing list, I should say. You obviously need the OpenCSD decoder. That again is on GitHub. What we have done is the debug tools team who were doing the AutoFDO research produced a highly detailed document on getting this running. That's in the OpenCSD documents area, and we've also put in there the record script that programs up the ETMs. And finally, obviously you need your whatever compiler you use and target system. Okay, I'm going to move on now to some of the more complex programming capabilities that can be done with CoreSight. So the first thing I want to talk about is the embedded cross trigger. This is two components, the CTI and the CTM. The CTIs attach to most of the CoreSight components. They either import or output hardware, single-line hardware triggers or other signals, and they're all meshed together in a star topology with the CTM. The CTM itself isn't programmable. It just provides the channel communications between all the CTIs on your system. Now, in general, CTIs and how they're wired are pretty much implementation dependent. We do have recommendations, and if you use a standard ARM core, they'll probably be done in a standard way, but designers can pretty much do whatever they like with the CTIs, and quite often do, other than the V8 architecture, which mandates a CTI per core and ETM pair, and also mandates the actual signals that they use, which makes things a little bit easier in that case. So a quick look at what CTI actually consists of. There are up to 32 input triggers, up to 32 output triggers. These can all be attached to one of the 4 CTM channels. They can be attached to one of the channels or all 4 of the channels, effectively signaling the rest of the system. Or they can also be gated so that the signals don't go any further than the local CTI and the local components. Finally, the channels can be signaled using software control as well, using the set, clear, and pulse registers, which will generate signals on the channels and any triggers that are attached to those channels. So just cover a few possible programming scenarios. Quite often, if you've got small buffers or you have a particular event you want to capture, it's quite useful to be able to stop the trace quickly. And using a hardware signal, we can achieve this without the usual latency of switching off all the ETMs and the ETR, and getting a lot of trace that isn't actually related to the event we're looking at. So effectively you need to program up the ETR is programmed to stop on a signal from the CTI. The CTI in the attached to the CPU is also programmed to communicate with that CTI, and then this can be triggered either by further using the ETM comparator, for example, or simply using a software routine in your application, or maybe the panic routine in the OS to trigger the CTI to switch on the channel and stop the ETR from gathering data. At which point, the normal shutdown procedures carry on, but you captured the event you were looking for. The system trace macrocell in general is used for software generation of trace data, but it does have up to 256 user-defined hardware inputs. Again, these can be used with the CTIs, and when you get a hardware input, it'll generate a block of trace in the trace stream, and if you use the CTI to stop the trace at the same time, you can actually, again, you can see the trace immediately that event happens. Finally, back to the ETM strobing, which we used in AutoFDO. This doesn't use any of the CTIs, but it does use more of the features of the ETM than are currently controllable by perf. Effectively, what we do is have a couple of counters running, and these you create a window for when the trace is on and a window for when the trace is off, and use the sequencer hardware to keep running this sequence over and over till the trace stops. Now, we did this with AutoFDO by creating a new patch to the ETM and a couple of additional driver features, which are translated by the driver itself. So you get a window size and a strobe size, which are translated into the 5 or 6 register rights that you need to actually set this system up. So at present, to use these advanced features, it's quite tricky. You can set them up by sysfs and then run capture on perf, but that's not well integrated. We did consider whether it was possible to actually perhaps get perf to set these up, but there's a huge amount of registers to be set, and it's just not practical. Patching the driver each time you have a new scenario, again, it is not really scalable because these are general purpose features, but you adding a driver feature each time you want to do something different isn't really a good way forwards. So what we're planning to do is create a complex configuration feature within the CoreSight drivers. This will likely be file-based, which will describe all the registers that need programming for your particular configuration, and this is going to be easier to add a single use this file command to the perf command line, and also be more usable standalone and for other applications. Now, there's also a couple of other things you can do with trace on Linux. Present, there's it's possible to do postmortem trace and debug, and that's been in the system for a while now. If you want to know more about that, there was an excellent presentation by Leo at the last Connect, and the system trace macrocell has been integrated with the kernel's software trace module, which has the same acronym, but that allows the kernel to output trace over the STM and into the trace buffers in CoreSight. So I'm just going to talk now a little bit about what we plan to do over the next 6 months, year or so. OpenCSD will need additional support for the upcoming architectures. I could possibly add 8.5 there as well, since we're now talking about it as well. Perf is currently being updated so that we support multi-core tracing. As I mentioned earlier, at present you can only do it per thread, which is a single core at once. The drivers, CTI drivers are in progress and will be upstreamed shortly, I hope. Need to see some more testing yet. There will be, I guess, some modifications for multi-core, and there is the complex configuration support I mentioned earlier. AutoFDO, the actual ETM patch won't be upstreamed. What we're going to do is use the complex configuration to replace that. But that patch will remain available on the perf OpenCSD site until such time as it is superseded. So we'll always have somewhere that people can try out AutoFDO for themselves. Finally, about, I think at the start of the month, the CoreSight designers and ARM produced the hardware specification for a standardised CoreSight architecture. This is to encourage the development of systems that have a standard set of components and make it easier for OS designers and software engineers to know that if they get a system that's compliant, perf just works, AutoFDO just works, everything that you expect to be there for CoreSight just works. I mean, this is primarily aimed at large Cortex-A systems, multi-core systems, sort of the application processors, not so much the M-class and R-class. So it defines a minimum functionality in terms of hardware and, to an extent, the firmware and system. So it has different levels for trace generation, capture, debug, requires ETM per core. Ideally, you want to be capturing to main memory rather than the ETFs or ETBs that we've used in the past. It requires that the power management of CoreSight be used by the normal operating system mechanisms. In the past, CoreSight systems have been switched on by the system control processor in Juno, which would only switch the system on if you attached a debugger to the JTAG port. Obviously, for systems that may not have that, we really need the OS itself to properly manage CoreSight power. And we do require that for it to be compliant, that CoreSight's enabled and accessible. So a level 0 system is typical of what we see today, and this is pretty much Juno or Dragon board or quite a lot of the cores boards that we see out there. You can get trace into the main memory via a router system MMU. It doesn't preclude having off-chip trace, but as part of the CoreSight-BSA, it's not required to have off-chip trace. So the future, there are some upcoming systems that look like this, and we would encourage everyone to sort of design and implement systems this way in the future, is to have effectively what would be a trace router and a system MMU, or at least a trace router and ETM. So you have a buffer per core rather than a shared buffer between all the cores. And this makes it a lot easier to identify which trace is from which core, and gets the system closer to what you see on something like Intel PT. And finally, so if you want to do all this, obviously you need to be able to enable trace on your platform. So you need to know, does it have trace hardware? Yeah, it's not going to work without it. But more importantly, is the trace hardware correctly described for the platform? And not just the trace hardware, but the power and the clocks and all that sort of information that enables the CoreSight system to be switched on. So if you can say yes to both, then you should be able to build a kernel and get CoreSight going. Now the problem we've been seeing a lot with a lot of platforms is that while they might have trace hardware there, it's very difficult to get the information from the manufacturers, etc. And so this is the biggest stumbling block we've had so far. So I'd encourage anyone who's designing these things, working with these things, to try and get the information out there so that we can get, as software engineers, we can get the CoreSight system working and get things like AutoFDO and perf working on your platform. So this is where we are at the moment. A quick summary of what's upstream, what's not. I think I've covered this quite adequately earlier. Finally, some resources. We've seen the OpenCSD before. Again, the perf OpenCSD for the newer patches. If you have any questions at all about OpenCSD, about CoreSight, about AutoFDO, or where to get things done, I would advise putting it on the CoreSight mailing list. And finally, if you want to learn more about perf on ARM, then I would recommend this training session on Thursday by Leo and Daniel. Okay, that's all I have. Any questions?
Do you have some testing tools to test whether a platform is properly set up, or how would you recommend test whether things are working as they should?
We don't currently have any testing tools. The difficulty is that if the device tree is correctly set up, then you can run the CoreSight. If it's not, then it's very difficult to say, is this right or wrong? It is a difficulty, and we would like to get at least some scripting tools to explore, see if we can see the system available in SysFS and try and run it up, see if we can get some trace out of it. But it is all very dependent on the engineer actually, or the platform landing team having set up the information in the device tree in the first place. So if the device tree is right, we can generally prove that there's a system working, but we can't sort of say, your device tree is wrong. It just doesn't quite work like that.
So just using perf kind of already helps there. Just use perf once and kind of do a trace, and then it's fairly certain
you can use perf, or you can actually just use SysFS to switch on one of the ETMs on the core and see if any data lands in the ETR. Okay. That's a basic level test where you say, well, there's some data there, so my trace system seems to be working.
The last step to build and boot a Linux kernel, will it be obligatory once the distros pick up a new kernel versions where the CoreSight drivers are checked in? Or is there a reason why they may configure those out?
Sorry, what was it?
So the question is, once distros will update their Linux kernels that they are shipping, will the last step to build a new Linux kernel with possibly custom configuration enabled still be necessary? Or distro kernels will eventually support that out of the box?
So everything should be seamless. You should just have to use it, regardless of the distro. So it should just work. You should not have, once we're all done with this, you should not have to recompile anything to add stuff.
Yeah, hi. I had two questions, and I'm going to try to remember the second. The first one was you had made a comparison against LBR, and I just kind of missed that. I was wondering if you could repeat it. And the second one was on the strobing. Is the implication that when the counter expires, you come back to the driver resets the counter, and then comes back down, so you have an interrupt from hardware to software?
No. Okay. The LBR, in order to determine whether we were getting the same results as we get from Intel, we did run some tests on LBR and Intel PT, and we found that once we got the system working correctly, yes, the AutoFDO was comparable. The results were as good as with Intel. The strobing is fully hardware generated by the ETM itself. The ETM has a sequencer, a hardware three-state finite state machine, so it just runs around those states and switches the trace on and off depending on which state it's in, up to the point where the application being run comes to an end, and then at that point perf will switch the trace off. But the strobing is fully automatic because it uses the features of the hardware. So there's no jumping between software and hardware in order to get the strobing effect.
And just follow up. So, and then when it's recording the samples, I mean, it's a PC every so many cycles. It's not 10 PCs in a row or something like that. There's a pair of counters in the ETM. So we set one to run for
5,000 clock cycles, and the other one then runs for a set of further 5 sets of 5,000 clock cycles. So effectively, when the trace is on, you run 5,000 clock cycles with the trace, then switch off for so many sets of 5,000 clock cycles, and then the state machine comes back round to switching the trace on for 5,000 clock cycles.
At 2 levels. Yeah. All right. Thank you.
So my question is, for the ETM, you can see that you just now use the strop to connect with the CTI to do the cross triggering. But for the STM, because the trace use the software method to send a message to the tracing data, but the tracing data is compressed. So we can how to know that the data is the match with specify the criteria, so we can trigger the stop all the other component. I mean that so how to connect use the STM with the CTI?
Because the STM has trigger signals going out of it to the CTIs. So in the example I gave, we were looking at a hardware input into the STM, but that can also, when that event happens, the STM can either, well, it will put a block of trace into the trace funnel that says, effectively trace data that says, signal number 553 has just gone high, but you can optionally program the STM to actually put an output to the CTI, which can then be transferred around the other CTIs and to trigger the ETR to stop tracing at that point. So you can effectively stop the trace as soon as that signal, and you'll know what signal's gone up, and if you've got the ETMs on as well, you'll have all the CPU trace going up to that point.
My understanding is that not every SoC has the STMs, the macrocells configured in. Is that correct?
That is the case. Not all SoCs have the same arrangement of components. And yes, some don't have the STM, and the hardware inputs are also implementation dependent. Some will use them, some won't. I mean, we have had customers who do use them, and one of this scenario I was describing here was it's effectively based on something the customer asked us, he wanted to do that. But yeah, that's the problem we're trying to solve by having the CoreSight Base System Architecture, to say we want all systems to have these components, and if you want to be compliant with the CoreSight-BSA, this is what you must have, so that when designers or engineers are trying to specify the product, they say, right, I want to get something off the shelf that complies with that architecture, therefore I know that it does have all the components I want.
And if I wanted to use AutoFDO right now, what machine should I get?
We've tried it on a high-key 960, but essentially it should work on any machine that can that does have trace, and that we have the necessary description to get running. So Dragon Board is possible, Juno. Like I said earlier, the difficulty we're having is making sure that we can get the information to get trace running on all these systems. Some manufacturers are more forthcoming with the information than others. I don't know what the reason for that is. I think it's just a case of the information is with the hardware designer, and by the time you get to software, they may not. It's more difficult to get at. But the systems we have used are the high-key 960, the Dragon Board, and the Juno. But any system that generates trace and into a local buffer as opposed to off-chip trace, we have seen systems that only have off-chip, which obviously is no good. But any system that is going to be able to capture trace, you can use FDO with, or AutoFDO with, yeah.
For ARM-V8, very important, ARM-V8, because we don't have decoding capability for V7 yet.
So just now at the first page that they have provided the share script record.sh to enable the strobe method. So with this share script, do we need other out of tree, the kernel patches or not? Or we, yeah.
Yeah, you'll need the strobing, ETM strobing kernel patch, and you'll need to get the AutoFDO tools from Google. But beyond that, no, you should just be able to put it all together and it should work.
And there's no magic. The only reason we have off-tree patches is because we don't have the complex configuration feature available yet. So we have to find a way to just make that configuration. It's the only reason.
Okay, thank you.